Okay. Quick. It's not a problem. To 10 to 30 to 30 to 40. This times. Okay, to 40 to 40.
Are we sure we want to be live streaming right now?
It's okay. The link is not active. Like it is active, but I don't saw anybody's there yet. Okay. Okay. Close.
Yeah, and I'll apologize in advance if you hear any beeping or any clanking in the background. We've got the warehouse that's attached right to the office, so.
Okay, I'm in the hospital.
Paul, are you going to be going to that TC workshop in Toulouse, or were you not invited?
To what? Apparently not.
Okay.
What was it that you were asking about, though? I didn't quite catch you.
So Mario Gozada and Rafael are doing a workshop with Zhao in Toulouse. I don't know if it's a leadership focused one or I just didn't know if you were invited to that as well.
Oh, not that I know of.
Okay.
Yeah, when is it?
That'll be next week, actually, on what is it, the 3rd and 4th. I'll be flying out to Paris this Friday. So.
Oh, very good. Well, my wife's coming home from there on Friday.
Lots of traveling around going on.
Yes, well, I got to cancel 2 of the 4 remaining trips this year, so I'll be almost stable.
Oh, Lord. I'm just crossing my fingers and hoping that they actually have the XCOM meeting scheduled at some time here in the next week. That way I can get that on my calendar. Oh.
Do we have another speaker in the waiting room?
He just sent a note saying he'll be on right now and that he could go first or second.
Okay.
Yeah, Dr. Tor should be here in just a second.
All right. And I don't see the speaker moderator from our side, but we have a plenty from other side. So
yeah,
I mean,
it will work out.
If Jim's not on, he said he could also go second. Doesn't matter. So
Okay.
Good to see you, man.
So
Hi, Tyler.
So let me, okay, we're just going to go very quickly through the organization of this. So this is my slides, and then we sort of, let's see, we have others. If we're 5 minutes late, it's not super big deal. Okay.
turn it off. Here. Be quiet.
Oh, we're setting up still.
No, I'm waiting for the last speaker to show up.
Ah, okay.
Because then I have to go over. I guess I'm too lazy.
Well,
And, you know, we'll do this French way. 5 minutes delay is just a way to kind of make sure that everybody pays attention.
right. Yeah, if it's all right, Paul, I'll just be reading from your wiki page to introduce you. So.
Oh, it's totally out of date. Yeah, please don't. Just say I'm a nanoscientist at UCLA who founded ACS Nano. That's fine.
Okay.
Yeah.
I'll just focus on that bit then.
Thank you.
Okay, so I guess, you know, why won't we just start with what we have and whatever we have. So again, for those who met the first time, I'm the president of the Society of Hacker Innovation. My job is to make sure that this will run smoothly. And I guess, I can be ad hoc moderator if my colleague Cisco will not show up. But I think we can leave this in the very capable hands of the Tyler and Linda.
Looks like Dr. Tor is here.
Yeah, okay. Did we admit him to our small gathering? Okay, perfect. So the way this works is that I pretty much opening the conference. It's 1 or 2 liner, why the conference happened, what is happening. Then we will talk about the organizers. So we have 2 of them, SHCI and the University of California, Santa Cruz. I wonder, Linda, maybe you could actually present both organizations very, very briefly, if that would be okay with you.
Sorry, I forgot to mute myself. Yes, I am happy to do that.
Perfect. So then we're going to do speakers. Tyler is in charge of presenting the speakers. Okay, and we talked that this Dr. Weiss wants to do it as short as possible. Okay, then we go to the moderators. I will do extremely short presentation of the moderators. Again, I still have to see if Dr. Gomez will show up. Then what I do, I will explain how you can access the conference. This is pretty much one-liner. Then we go over the format. So this is the modified format. Everything should be closed in 10 minutes or even shorter. Then we do the presentation. Who goes first? Dr. Weiss, right?
I think Dr. Tor.
Okay, so Dr. Tor is going the first one. No breaks. Dr. Weiss goes with his presentation. We will wrap everything by 2:40, 2:45, and whatever time we have up to 3 o'clock. This is the moderator Q&A. We do not have a break room. So that's our sort of lineup over here. Then I'm going to introduce that. So I'm keep talking. Then I'm going to talk about the net ticket we have here. I will modify in a second for the break rooms. And then I'm going to hand this over to Tyler, and Tyler will ask the first presenter to present, and up we go. The way this works the most efficiently is every time if you want anybody to do anything, just use the name. So I will literally say, Linda, can you introduce the organization? So there's no confusion. And the same way, Linda will say, Chris, over to you, so on and so forth, or Tyler will say, Dr. Weiss, please start presenting. If there's any problem, again, I'm here to sort of solve that problem. We have a free co-host. We're recording this in the cloud. So that's the sort of big plan. Any questions?
Just a quick little housekeeping thing from me. I will send a direct message at 15 minutes in and 19 minutes in. That way it helps you guys pace if you're going to go up to the 20 minutes.
Okay.
Could you repeat that?
Yeah, so what I'll do is I will send you guys a direct message at about 15 minutes after, and if you go beyond that,
okay.
I'll give a 1-minute warning as well.
I got it. Oh, okay, but we have 20 minutes, right?
Yeah, up to 20 minutes.
Okay, got it.
All right, perfect. So I started meeting the people, and then we do 2 quizzes, and then we start. All right. Hello, everybody. We're going to slowly start the conference as we're waiting for all the stragglers to show up. Let's do the first kind of poll, just to warm it up. When do we think that we're going to be next pandemic? All right. So looks like 2030, or I can tell. Let me share the very quickly results. So let's do it. This is what we got. And we almost have everybody. Let's do one more quiz, and then we sort of go on with the presentation. So what do we think about how the COVID affects the innovation? What is the most promising and most hype technology? Yeah, let me.
Oh, Chris, I may have accidentally. Yeah, there we go.
So, okay, let me see if I can redo it again. Now, I think you by mistake
There.
close it. Okay, no problem. Then we're not going to worry about that. Okay, so we're going to start record. We're going to put this on the YouTube, and let me start the presentation over here. And then we will go on with our fantastic conference. Perfect. So welcome everybody. My name is Chris Waldansky. I'm the president of Society of Healthcare Innovation. In my other job, I'm actually a critical care doctor and anesthesiologist. So you may hear some noises from my hospital in the background. I couldn't get myself out of the practice, something about the pandemics and the shortage of the people. I'm also innovator. I also work in the field of the nanotechnology, but nowhere even close to the expertise of the people who are going to be moderators and most important presenters. Innovation Frontiers 2022 is the conference about innovation, but what are the unintended consequences of the innovation? What can go wrong with the innovations? Where are the potential dangers? This is our subject, and part why this conference is so important, this annual conference that we organize every year, is that I was actually inspired to make this conference by our fantastic collaboration with University of California, Santa Cruz, especially with Linda, who brought to my attention a lot of issues related to the innovation. I let the Linda now to present both UC and SHCI in brief scope. Linda, over to you.
Thank you, Chris. As you all may realize, the University of California, Santa Cruz has at its heart social justice and making the world a better place. And within Crown College, within UCSC, is generally thought of as a science college, but it's multidisciplinary. And the mission of it is to promote intellectual, personal, social success with ethical and inclusive living. We have a really diverse community. It's a great place to be. Love being a part of it. And we're fortunate enough to have connected with Chris and the Society for Healthcare Innovation, which is an entrepreneurial, innovative professional organization comprised of physicians, nurses, healthcare executives, tech and exec leaders, with working towards a unified ethos and with the mission of improving healthcare through innovation and creating access. Back to you, Chris. Thanks.
Thank you very much, Linda. This was a very good presentation. So the next this is the most important part of the talk, is our speaker. And again, we have speakers because of the Tyler, who is sort of working for both organizations. Tyler, if you can introduce our fantastic speakers, please.
Yeah, thank you. So I'll introduce them in order as you see here. So Dr. Tor is a synthetic organic chemist. He is currently at Rice University. He is very focused in a lot of different areas of nanotechnology. So when it comes to graphene electronics, silicon oxide electronics, he's also done a lot of work into, if memory serves me right, mitigation of chemical weapons as well. So really looking forward to his talk here. He's also had several different awards, obviously nationally renowned scientist, been at the top of the most important scientist lists for a variety of different journals and various different websites as well. Dr. Weiss, he is at UCLA. He also is the founder and editor-in-chief of the American Chemical Society Nano, so ACS Nano. His laboratory does a lot of varied work as well. I know that they've dabbled into neuroscience. They've been dabbling into monolayer lipids. So he's also a chemist by trade. So thank you both for being here with us today.
Thank you very much, Tyler. So let me introduce the moderators. Moderators in those meetings are charged with pretty much channeling the ideas put by the presenters. We have two of them. Tyler Gines is a colleague of mine. He works for the AAA. He has a PhD in the philosophy I have to admit that being a doctor, he always makes me feel small the second he starts talking, but this is just my ignorance. The second moderator is Cisco Gomez. He's a colleague of mine who currently works as a neurologist and program fellowship director at the University of Missouri. So those are moderators. What we're going to do today, we're going to have a presentation which is actively streamed on the YouTube and also on the LinkedIn. This is again thanks to Linda and News of Santa Cruz involvement, which actually makes this into the educational experience on top of us as a society and the institutions sharing this with the professionals around the world. The way this is going to work, we're about to wrap up our introduction. Then we have a two presentation by speakers side by side. I believe Dr. Tor starts, and then we move to Dr. Weiss. Then Cisco and Tyler will provide the Q&A, and at 3 o'clock we will have a sharp closing. Couple details. We live in the post-pandemic era, but everybody remembers Zoom is the great thing. So mute your audio if you don't talk. Make sure that your background looks better than IKEA. Don't show too much of your dirty laundry, so to speak. Background noise is sometimes a problem. We'll not have a break room, so don't worry about the guidelines. But the guidelines are simple. Like in every conference, we try to be civil, and that's pretty much self-explanatory fact. And please remember that all the conference sessions are recorded and will be shared with the other people. So this is our plan, how we're going to work. I'm going to stop sharing and I'm going to hand this over for the first presentation. Thank you very much.
Thank you. Let me share my slides here. Okay, so I'll tell you some of the nanotechnology work that is going on in my group. And it's all embodied in this one slide. So there's very few slides in this presentation, and this is just sort of a collage to help me to discuss this. First topic that I'll mention is work that we do on laser-induced graphene. We learned that we could take any surface, any carbon surface, and convert it into graphene by hitting it with a laser. The type of laser is a 10-micron laser that is found in every machine shop. So every university has one of these, and a lot of homes have these. And so this is on a piece of polyimide. This is on a piece of bread. We're not dropping graphene down on the bread. This is converting the carbohydrate strands of the bread into graphene. And you can make any pattern you want. This is a coconut, and we made a supercapacitor out of the coconut shell. So just to give you an idea of how big this is, in 2021, which is the last year that I have the statistics, there were 450 papers that were working on, came out where the topic was laser-induced graphene. And there were probably another 200 papers that didn't call it that, but it was the same idea. So this has really taken off. We discovered this in 2013, first published on it in 2014, and now there are just hundreds and hundreds of papers coming out on this. The first product from this is this. It is called the viral wall. Inside this little box is a sheet of graphene. When these people speak, the air is drawn into this. And then when the people on this side speak, their air is drawn into this. And then it goes through this sheet of graphene, and which captures 99.9% of the SARS-CoV-2 virus in a single pass. And it's not just for viruses. It originally made it for bacteria, and also the bacteria byproducts like endotoxins that float all around in hospitals. And then fresh air is blown up. So you have a virtual shield of graphene between the two sides of the table, in a sense, because fresh air comes out the top. So that's the first product that's come out of this. This is graphene nanoribbons. We learned that we could make graphene nanoribbons by the splitting of carbon nanotubes longitudinally. And they split longitudinally to form ribbons. And I'll show you more about the applications of that in a moment. These are sold by a company called Sigma Aldrich. This is memory that we've made, silicon oxide memory, and that's now in a company called Weebit, and that is now a public company. and they are now producing this silicon oxide memory. It is a 2-terminal memory rather than a typical transistor, which is 3 terminals. We work a lot in the area of traumatic brain injury. We've done a lot with that, and so we can take what would normally be a brain that would look like this and have it come out looking something like this. But this is a brain that has had hemorrhagic shock, very little direct damage to the brain. But if you have TBI, you see slight damage, the traumatic brain injury. But if there's traumatic brain injury coupled with hemorrhagic shock for 60 minutes, you see that you lose a large part of the brain. And we've developed a number of nanoparticles, and that's in a company now called Gerinox, and that we've started, and that's to help to develop that for TBI and for stroke. TBI and stroke are very similar in the way they work. We've done a lot on the growth of carbon nanotubes directly from a graphene sheet. And then what that does is it gives you a very high surface area electrode. And we've developed that now, and that's now in a company called Zeta Energy. And that's in Houston here. And they're in a Series B financing state, and they're making prototype batteries that are getting sent out to lots of battery testers now. And so this is it's a lithium battery where they've controlled the dendrite and the mossy lithium formation, coupled with a sulfur cathode. And the first product will be 1.5 times higher specific capacity than a typical lithium-ion battery. And it charges also in 10 minutes. These are graphene quantum dots. When we started our work in the area of graphene quantum dots, they were selling for $1 million per kilogram, $1 million per kilogram. We developed a process of making these from coal, which is $60 per ton, and we could make these in 25% yield in one step from coal, because it turns out that coal is filled with small pieces of graphene. We learned how to isolate that, and that's now in a company called DOTZ, D-O-T-Z. It's a public company now, and they use it for anti-counterfeiting. It's for marking of items, so high-end women's purses, shoes, so that you can authenticate it. And then you put a little handheld UV light and you can see the light pattern, and it gives you a response whether that's indeed the light pattern of the mixture that was used when that was made at the factory to authenticate that product. We've come up with a way to take plastic waste, which is a big worldwide problem, and we can decompose it into oligomers and then repolymerize, or what we do is we carbonize it, and we've turned it into a material that can trap carbon dioxide. So we take one problem, plastic waste, and we use it to solve another problem, CO2 capture. And this is CO2 capture for flue gas. So you have these power plants, and so it works very well where you have lots of nitrogen there and lots of water coming out as well. These do not decompose in water. And we've gotten up to about 16 weight percent at 0.1 atmospheres of pressure of CO2, which is about the pressure of CO2 that you get out coming out of a flue gas, about 10% CO2. And so that's a project for us. This is now in a company called H2 Blue. This is where we can take any carbon material, any carbon solid, we put it between two electrodes, we would put a high voltage, high current through it. There's a big flash of light, and whatever is in here converts into graphene. So whereas this was putting graphene down on a surface to make devices out of it, this is making bulk graphene. And this was a little automated system that we built during the COVID shutdown. We were out of the lab for 2.5 months, and we built this system. I sent 3D printers home with the students, and so they built this. The other parts were all purchased off of Amazon, and that allowed us to fulfill our Department of Energy goals, which was to go ahead and produce. We had to produce 1 kilogram in a day of graphene from coal, and we turned out we could do 1 kilogram in an hour and a half. This is now translated into a company to go much larger scale, and they hope to be at a ton per day in about 3 or 4 months from now. And so that really will change the dynamics of the graphene market. That graphene is going to be going into cement and concrete, plastics, wood composites, flooring materials, so many applications that will be derived from that. We have another area that we work on, and this is called nano cars, where we're able to build single molecule cars. Each car is one molecule. And you can see one of the cars here on the surface. This is by STM. This is with one of Paul Weiss's former students did this work with us, Kevin Kelly. And you can see the car with its 4 wheels. It's going to turn and moves out across this surface. And this was actually the first nano collision ever recorded. These are 1 atomic step high islands on gold, and this is running on a gold surface. This was a non-motorized nano car, which was drawn by the field gradient from the tip. So the tip wasn't pushing it, the tip was in front of it, and you apply a voltage, and there's a field gradient, and the car starts following the tip. Then we built cars that have these motors on it. These are Faringa motors, and we constructed these into the chassis of the car, such that when you shine light on it, the motor spins unidirectionally. And it spins in only one direction because there's 2 elements of chirality here. So the 2 directions would be diastereomeric. And so there's one is favored over the other. And it pushes it along the surface. And this motor actually spins at 3 million rotations per second. So one of the things that we've done in medicine is we've taken just the motor and we've attached on peptide addends to recognize particular cell surfaces, such that when the motor associates with a lipid bilayer, then what we do is we activate the motor by shining a light. It will spin at millions of rotations per second and drill a hole in the cell membrane, ending up killing the cell. This is a superbacterium. This is a gram-negative bacterium, so you have a double membrane here, plus a peptidoglycan layer in between. And these just drill right on through it. They just drill right on through it, and the whole cell blebs. And this happens in seconds. In 30 seconds, these have just drilled into it. And so this is something that these bacteria, it's going to be very hard for them to keep this from happening. And the reason is this is a mechanical action at the molecular scale. So it has great utility. We're going after it with cancer now. We have other molecules we've built that are, rather than being excited in the UV or the visible, now we can excite in the near IR. So now we can get much better depth penetration in medicine. And those are using what we're calling molecular jackhammers. We have another area, and it's in the environmental space, and it's using this same methodology where we put a high voltage and a high current across something. And this is a mountain. This is a mountain of fly ash. Fly ash is the inorganic residue that's left after burning coal. And it turns out that fly ash has a lot of rare earth elements in it. And so what we do is we put the fly ash between 2 electrodes, we flash it, and now the rare earth elements come out because they're usually in a aluminosilicate glass from the furnacing process it's been through. But now that glass breaks because in this flash process, it heats at 10 to the 5th Kelvin per second and cools at 10 to the 4th Kelvin per second. The glass breaks, and also there's carbon in there. And so the rare earth element phosphates reduce to the rare earth element oxides. And those are much easier to dissolve than the hard to dissolve phosphates. So we get twice as much rare earth elements out using just a very dilute acid stream, a 0.1 molar HCl, as opposed to the 12 molar HCl that's normally used. Similar waste material is something called red mud or bauxite residue. It's the residue that's left after production of aluminum. And that too has a lot of rare earth elements in it. So we've demonstrated where we can pull the rare earth elements out of that. So these are 2 big environmental problems where you have these. And what happens is when we get the rare earth elements out, we also get the toxic metals out. So there's a big advantage. These are printed circuit boards, and these printed circuit boards just stack up particularly from server farms when they replace them every 3 years. And these are full of many precious metals as well as toxic metals. We can flash out the precious metals, we add halogen, and these flash out, we bring it out as the metal halides, and so they just come distilling right out of this reactor. We have a slightly different design for this, where the volatiles can come distilling out. So we get the precious metals and we remove all the toxic metals such that these become so clean, whatever is left over can be used as agricultural soil in California. So that it really pulls out the metals from this. We're doing the same thing in soil remediation. You can take soil that has been either has heavy metals in it. You can remove the heavy metals. We can remove the toxic organics, and we're also doing that now with PFAS, these perfluorinated alkyl substances that are a real problem. These came predominantly from firefighting foams. And then we also have where we're recycling batteries. We're able to recycle the anode using this flash methodology, and we're also able to recycle the cathode using the flash methodology, using much less acid than these other methods. So these are some of the prospects of the nanotechnology we're doing. Now, this is a rat. This rat has had its spinal cord completely cut in two at the base of the neck, complete transection. We put 1 drop of those graphene nanoribbons in that gap at the base of the neck, and it's a 1% solution in polyethylene glycol. And then we stitch it back up, and then after 2 weeks, the rat gets up and starts walking again. That's with a totally cut in two spinal cord. And the rat scored a 18 out of 21 on a mobility scale. 21 is optimal mobility. And then you will see this transition now to 3 weeks. And at 3 weeks, she's doing quite well. And she can run, and you'll even see her kind of try to get away from us here. As she goes, as they try to put her back in the cage, she'd kind of try to run away there. And so she's doing quite well, scored a 19 out of 21 on a mobility scale now after 3 weeks. And so these are being investigated now for spinal cord repair. So with that, I'm going to begin to wrap up. This is the research group, the folks that we work with. And these are the people that have done the work. I don't get in the lab and do anything anymore. I'd probably hurt myself. But these are the folks who do the work. And you can check me out at my website, jmtour.com, or I've got a YouTube channel, Dr. James Tour, and you can check me out there. And with that, I will stop sharing and turn this over to Dr. Weiss.
Thanks very much. Let's see, get that on. Is that the right screen showing? Good. All right. So, along the theme of the meeting, I wanted to make a pitch for not all unintended consequences are bad. And so one of the advantages we have at UCLA is all of science, engineering, and medicine are around one courtyard. We're actually the smallest of the UC campuses by area, but the largest by any measure of population. So we see each other a lot. And for instance, in the Nano Center, where I formerly served as director, we had the leading nanotoxicology center in the world. They like to call it Nano Environmental Health and Safety, but you get the idea. And oftentimes in testing materials, there were positive aspects that could then be turned over to, it was basically the same people in the room who were in medicine, developing delivery vehicles for nanomedicines and so forth. And so those cross terms turned out to be particularly valuable. And I'll mention for the trainees especially that you're getting something very special out of your training in nanoscience. So at the 10th anniversary of the National Nanotechnology Initiative, the White House asked us at ACS Nano, and I will point out I'm no longer the editor-in-chief. I finished my term at the end of last year, but we were asked what it is we've done with over $1 billion a year in funding and what we might do if that funding were to continue. So those seem like two important questions to answer. And, you know, we answered the scientific side of that, but more relevant for the discussion here, perhaps, is that the field had developed by people coming together from chemistry, physics, engineering, materials, medicine, toxicology, data science, and so forth. And we shared problems, approaches, tools, developed new tools together, developed new languages together. And when we looked in detail, we realized that set of communication skills was unique among fields. And if I had a longer talk, I might, you know, bash my wife's field, where in neuroscience, that kind of communication was never developed, even though it should have been. But we'll get to the Brain Initiative, you know, as we go along, which was actually a proposal that came from a nanoscience team that I put together for the Office of Science Technology Policy. And we had to, you know, convince the neuroscientists that they shouldn't try to kill it. Okay, so actually, Professor Tour and I worked together for many, many years, and our lab was best known for looking at the ultimate limits of miniaturization, the smallest switches and motors in the world, many of which he synthesized. You heard a little bit about the nano cars that Kevin Kelly, a former trainee in the lab, worked on in a joint center that we had together. And in order to do that, we had to develop two sets of capabilities. The first was a set of microscopes that could measure structure, function, and spectra with better than atomic resolution, many tens and hundreds of thousands of times on the same structure, whether it's a molecule or assembly, not really relevant to today's talk. But what we developed as well was the ability to place those single molecules or assemblies into controlled environments to study them, to be able to stabilize them. We could even design hydrogen bonds down to 1/10 of an angstrom between the functional part of the system and the surrounding matrix. And we could do that from the submolecular scale all the way out to the centimeter scale. And so, you know, we were basically doing this nanoscale physics experiments when one of my neuroscience colleagues at the time, I was at Penn State, Professor Ann Andrews, came into my laboratory and said, you know, what you're doing might actually be useful. And that was both, you know, insulting and flattering at the same time. So I asked her what she meant. And her goal when she left the National Institute of Mental Health was to develop sensor arrays to listen in on chemical communication in the brain. And her favorite neurotransmitter, since she studies anxiety and depression, is serotonin. So she asked us to put serotonin every 5 nanometers on a surface to which otherwise proteins and other biomolecules would not stick. And I said we couldn't make a grid, but using the self and directed assembly technologies we developed, we could make sure no two were next to each other. And on average, they were 5 nanometers apart. And that really led to the chemistry part of the Brain Initiative, where she started that project in 1998. We joined in 2002. And last fall, we did the first measurements using that technology in the brains of live behaving animals. It was a pretty long time to reach that milestone. And then in addition, many people measure voltages, for instance, and try and listen in on that communication. That took me, actually, we later, after we started working together, we later got married. We moved to UCLA together in 2009, where I saw this opportunity for nanoscience and medicine. She saw this opportunity of 500 neuroscientists to work with. And actually, our hospital is at the end of the block. And indeed, my fantasy of contributing to human biology was even, not as optimistic as real life turned out to be. And so I'll tell the story of one postdoc who came to our group, whose background and clinical work is in pediatric hematology oncology. And he was in a special program our pediatrics department set up, where from his residency, he got a fully paid, it's called clinical fellowship, but basically a postdoc, and then guaranteed a faculty position in our pediatrics department, which is one of the top medical schools in the world. So that was kind of cushy way to go. Then he we batted around what it is we'd like to do over that period and settled on what we would like to be able to do is to be able to treat patients with genetic diseases like single base mutations. Sickle cell is one example with 300,000 patients a year, mostly African and of African descent, or thalassemias, another 300,000 patients a year, mostly South Asian and South Asian descent, patients. And then there are a whole host of, rare immune diseases and so forth. And we want to do that safely and economically in an hour while a patient was in the office, and do it without viruses, harsh chemical or physical treatments, because we'd be treating hematopoietic stem cells, which are, delicate and precious, basically. And we have the advantage that we have all these folks we work with who in their clinical practice do bone marrow transplants. And so instead of, wanting to publish a paper with a cell that turns green, they actually want to get these treated cells into patients. And they have the many years or sometimes decades of expertise of having the model cells, the animal models, the patient cells, and ultimately the patient. So Don Cohn, for example, was the fellow who cured bubble boy disease, severe combined immune deficiency. And when our technology developed to the point where they were showing up in my office and asking us to work on their diseases, I knew we'd hit it. And then on the other side of the house, whenever we saw an opportunity for a new method, we just called up the top engineer in the world in that area and asked to work together. And I'll show work with Tony Jun Wong, but we've worked with many others who I show here. And Tony had been is a UCLA alum. I was his mentor at Penn State before we each left. He's now at Duke, and we sent 4 students to his lab and made our idea work within a week, which is not how our microscopes work in the physics part of my lab. Okay, that also led us over to doing liquid biopsies to follow, basically do diagnostics of disease and diagnostics of how treatments are functioning. I won't have time to talk about it, but these turned out to be coupled more through the people we worked with. And then we developed technologies for one particular disease where we had half the patient population of the United States and some special knowledge about what's on the outside of the cells that are sloughed off in when the cancer is metastasizing, but that technology will be more broadly applied. And then we've moved even from there into tissue engineering. I won't have time to talk about that. If people are interested, please contact me. And so we got to this, as I mentioned, from this idea that we could isolate individual molecules. And we did this with Professor Tour to look at his rigid molecules that function as switches. The people who developed these self-assembled monolayers recently won the Kavli Prize from the King of Norway. I was honored to go see them and help with that a little bit last month. And really, as I mentioned, there's a direct line from that and the chemical patterning to the sensors that Professor Ann Andrews developed and to this brain initiative that we developed. And the technology roadmap for that was developed by this nanoscience team. But what was particularly useful was bringing in neuroscientists and others who worked across biology, synthetic biology, other fields, anyone we thought who could be useful in contributing ideas. And we took reference from the Human Genome Project, where it was pitched as you'd read the book of life and you'd cure all diseases. Didn't work out that way. Right. But what we did do was develop new technology that let us ask new questions. And that was really all in the last 3 years of that project, where the brute force approach was abandoned and the new technology, the high throughput sequencing, was what has really had impact on the world, where we can compare, 100,000 individuals or 1,000 different species, where we could ask questions that would just have seemed, fantastical in the early days. And in fact, so this is just an example of some of Van's work where we had to develop special technology that merged electrical engineering, molecular recognition, neuroscience. And then it applies actually very broadly across disease diagnostics, wearable sensors, and many other areas. And after the brain initiative, there was another one you might not have heard of called the Precision Medicine Initiative. And it was viewed as a failure by the White House because the people involved basically just said, give us more money and we'll go do it. And that did not get the kind of public attention the Brain Initiative did. And so for the Microbiome Initiative, the third and final one of the Obama White House, they actually asked us as nanoscientists to come back and to lead the technology roadmap and to bring in everybody we needed. And that included soil scientists, atmospheric scientists, oceanographers, dermatologists, gynecologists, GI doctors, data scientists, and, some of our sensor people too. But the microbiome was, arguably much less nano even than the scale of function in the brain, which is what brought the nanoscientists into it in the first place. And as Anne has said for many years, the scale of function in biology is the nanoscale. So we have these special opportunities to interact, to measure, and even to stimulate. Oh, why am I not advancing here? Well, that's not good. Let's try going up here. Oh, turn that off. For some reason, my slides aren't going to keep going. Oh, there we go. Got it. All right. So just one quick example of a story. The idea, if we wanted to treat a 12-kilogram child, is we need 1 billion hematopoietic stem cells treated. The neat thing about those is, when you take them out, all you have to do is ablate 10 to 20% of the bone marrow. It's not like a conventional bone marrow transplant where, you get 2 tries and then the patient dies if it doesn't work. We can do all that gene editing work ex vivo using the gene editing technology like CRISPR-Cas9 that's been developed, and after sorting the cells. And then all we need to do is inject the cells intravenously, and they'll go through pores in the bone marrow and back into the patient. I will point out that for cancer immunotherapy, CAR T cells, the same technologies work. We only need about 1/10 as many cells. I have a limited amount of time, so I'll just mention, how we're doing it with hematopoietic stem cells. The competing technologies are basically electrocuting the cells to make holes in them, to give harsh chemical treatments, which you definitely don't want to do to stem cells, to use viruses, which have a problem of possibly turning on oncogenes and giving the patient a rare cancer and killing them. And also, actually, that's a laboratory cost, $100,000 for a patient prescription. It's between $500,000 and $2 million a dose. Not safe, not scalable economically. And then out of the Langer Jensen and Anderson labs at MIT, they had this idea of squeezing cells through a constriction and microfluidic channel, which opens up pores, but their channel's clogged after about 1,000 cells. So they're about 1 million times too slow. So we came up with a bunch of different ways to make channels not clogged. My favorite is one in which we use acoustics to define a virtual channel. The pioneer and expert in that is Tony Huang, who I showed earlier. I sent 4 students to his lab after we had this idea, and we made it work within a week. We can do it in one of 2 ways. We can have a virtual constriction in the middle of the channel and, add the payloads to the cells, or being a basketball school, we can electrostatically attach the payloads to one wall of the channel, and then we can use acoustics to bounce the cells off. Our viabilities are very high, more than 90%, way above what one gets from electroporation or the liquefaction. And our efficiencies, depending upon the particular cell type, are in the 25, 30, 40%. So comparable to the other methods. But since our viabilities are so high, we can also multiply cycle. And so we can boost those up further if we need to. And in fact, the FDA looked at our technology when they saw our paper, and they got in a fight over who would make the decisions on approvals, and then just reached out to us and said, here's the question you should ask us that will make us decide which way to take in a fork, and then come back from there. And in fact, Don Cohn already has approval to go into patients with sickle cell disease. And they told us the route we could take to use his approval once we show we're at least as safe and we're at least as effective as electroporation, which is the way the approval went. Okay, and so these are just some examples of how it works. I think I have a little movie here that will hopefully go, maybe not. There, yeah, there we go. So you can see him slamming into the wall, just a few of the cells. And the nice part about the acoustics is, unlike the constrictions, we have to make a different one for each cell type. We can just change the waveforms in the acoustics and make this work. And in each case where we do any of these transfections, we work with Steve Young, who's an expert in getting into the nucleus. And so we check that we always get the payloads in the nucleus. And the nice way that the particular payloads we have are constructed is we can include DNA, RNA, protein machinery, and the pixie dust that helps you penetrate into the nucleus. And we can use much larger payloads than the viruses can. And those were developed by our colleague and collaborator here, H.R. Tsang, in pharmacology. They uses host guest chemistry. It's actually relatively simple and all kind of approved components. So in order to test the idea with immune cells, we used a mixture that included T cells. We actually get much higher efficiencies if we use purified T cells, and these are human cells. And then we did some initial experiments on the human hematopoietic stem cells. Again, our viabilities were plenty high, and we reached 25% in just our very first data. It's about $5,000 per set of cells for these experiments. So we optimize on some others, and then we come back to the human hematopoietic stem cells. On the other side of that, and with the same cast of characters, as I mentioned, we do this disease monitoring with liquid biopsies, but we won't have time to talk about that. That's the group. Okay, so I tried to put everyone's name on every slide as we went along. We have collaborators around the world. When we've reached out to people to collaborate on any of these ideas, N-1 of them have said yes. And the one who said no several years ago came and visited about 3 weeks ago and apologized for saying no. And so it's a really fantastic way to work, where you come upon a problem and you go after it. I'll point out that before we had any data, all these pediatric cancer foundations stepped up and together, put $2 or $3 million together. So we get a group of 15 people going after this. After work, the NIH came in, and Steve got this award from the NIH director to launch his independent career as an assistant professor in pediatrics. And he's here now as my colleague. And our MO is to basically to look for unsolved problems, and particularly the MDs and MD PhDs in my group, when they're doing their rotations, they're looking for, well, if I had this diagnostic or this device or this therapeutic for this patient, I could have treated them, or I could have treated them better. And so then they come back to group meeting. Oops, we have a poll coming in here. They come back to group meeting and either explain a proposed solution or just throw out the problem, and other people in the group come up with solutions. The first one who came up with a solution with gene editing was actually mechanical engineering postdoc trained in polymers and nanolithography. And we made that one work as well. And we're trying to institutionalize that now. Might be an interesting part of the discussion where, instead of senior faculty learning all these skills for, being on the advisory boards and solving other people's problems, and some of them coming back and applying that to their own groups, it works perfectly well to start with creative graduate students and postdocs and undergrads and junior faculty, and expose them to the most important problems in the world and ask for their ideas and develop that capability in terms of, finding the right collaborators to go after. That's a great way to get out of bed. I can't wait to get in the lab to solve this problem that I care about more deeply than anybody else. And that's how you get a job later, saying, here's the most important thing to do, and I'm the only person who can do it. Or if you're at a company, saying, here's the most important thing the company could do, and I need these resources and these people in order to make it happen. So we're applying that idea now. I'm just the last couple of slides to talk about the UN Sustainable Development Goals. We've put together a network. I'm the founder at UCLA, the other leaderships at Sydney, Waterloo Institute for Nanotechnology that's organized around these goals, the Botswana Research Institute, as well as Mesa Plus in the Netherlands. And there's a funding agency in Japan that's been supporting us. And we're growing this network. I encourage you to have a look at this paper that was in the last issue of ACS Nano, where I served as editor, or, have a look at this network, which we're now growing. And I'll be spending the first half of December going around the world working on this. So thank you so much, and happy to continue the discussion, and appreciate you putting all this together.
Thank you very much. If I may, let's hop right over into questions. I've got one prepped, and I'll serve this off to both of you. I'll have James go first. That way Paul can gather his breath a little bit, maybe get to drink water. But first and foremost, I guess I want to ask, so in your respective areas of research, and I know you might be leaving this more to the grad students than anything else, but what do you see as the greatest ethical challenge that's present in your respective fields? And again, if I may, Dr. Tor first.
Well, nanotechnology, from my perspective, has been looked at more closely from its origin, from its point of origin, than any other field. So generally, you have a technology and it messes up the environment, and then you go and you try to catch up on things to try to clean it up. I think in nano, right from the beginning, in the early stages of nanotechnology, and I'm talking 25 years ago, people started thinking about what the dangers could be. And there are these centers that have started to look at this. And we treat everything as if it's going to be toxic and dangerous until we know otherwise. And then we do, of course, the cellular assays to study toxicity, and then we move on up from there. So some of the, I don't have a lot of ethical things that I feel that have been showstoppers for me, because we've addressed them, and we always try to get the proper approvals and to get other committees looking at it if we're going to be moving toward live animal studies. We treat everything with respect. We don't release it. We don't release it to the environment until we've really studied this and looked at the effects. So I wish I could give you more specificity, but that's about what I know.
And then if I may, Paul?
Yeah, I would say, very much what Professor Tour just said. I would say the more forward-looking places working in nano have looked at life cycle and said, okay, where is this going to be used, and what's going to happen when we're done with it? That hasn't been the case, in the chemical industry, semiconductors, automobile industry, and so forth. People, as nano is developed, relatively late compared to those other areas, I think we benefited from seeing the failings in other industries that have caused a lot of damage. And we can, as we're looking at the commercial opportunities, also then say, okay, well, let's reverse engineer it and make sure that we can do safe by design.
Let me ask a follow-up really quick, and then I'll pass it over to Cisco maybe to address some questions that are coming through chat. But branching off of that, what direction, if any, again, understanding your expertise in this field, would be beneficial to help change some of the maybe negative narratives, or again, any showstoppers that might be present right now? I mean, I know nanotechnology education is very limited for a lot of different people. Some people are familiar with it through, say, the Discover channel or what have you. So I guess for at least the emerging generations, what sort of narrative would you expect to be useful specifically for the healthcare application?
Right. So yeah, let me start on that. I think that's an excellent question. And, we have a very small fraction of the people in the US who send their kids to science camps and take them to museums and so forth. And it's really important for us to reach the general public, to reach the, decision makers, which are not always representative of the general public, as we know. And so, the question is how one does that. One of the approaches, we have, again, a special opportunity here in that we're in the center of the entertainment industry. So we have a collaboration with the Directors Guild, the National Academy of Sciences, to get science advisors into movies, TVs, and films. That we're not police. We don't say the science is wrong here. We bounce ideas off people. We let the people who are doing the writing and directing and so forth know what scientists are like. And actually, we have a lot in common. They have OCD. Everything has to be just perfect. They're looking for money all the time. And as soon as you get over the you're so rich, you're so famous. I mean, you're so smart, you're so famous. Not scientists are rich. Couple exceptions, sorry. So I was just on a startup call before this, and it's all Jim's companies. As soon as you get over the you're so smart, you're so famous thing, then you can get right down to it. And there's actually a lot of symbiosis, and it's fun. I've done about 10 or 12 of those, and to have some insight into where a film might go, or even a set of movies or a TV show. They're looking for some angle, and they're fine taking artistic license with what you say, and those have ended up becoming long-term relationships. And I think by placing science in somewhere where everybody's going to see it, we have a big advantage. And nanomedicine's example, an example we had, there's a long way from fantastic voyage to what we could do. Yeah. In fact, we tried to get Rekha Welsh is around here. We tried to get her to come and do our gene editing, for one of the cancer foundations, but we couldn't get past her agent.
And then,
So
if I may,
she's
Dr.
on. We thought that'd be kind of fun way to promote, here's a way to treat all these kids with leukemia or other diseases. Yeah.
And then, if I may, do you have anything to add, Dr. Tor? Maybe a unique perspective there?
I've tried over the years several things. I mean, I came up with an idea to get into the schools, and we coupled it with Dance Dance Revolution and Guitar Hero, and made it all free by download. And it turned out to be the biggest science attraction in the state for education. We had over 1 million downloads in the first year, 40,000 teacher downloads. So lots of people used it. Now I've just over COVID, I started a YouTube channel, and so putting out YouTube videos. I posted one a few weeks ago, and it's got over 125,000 views.
Would you please put the links into the chat or send them to us later?
Yeah,
I'd
it's
love to see them.
Dr. James Tour is the YouTube channel. Dr. James Tour, all one word. So if you just go to YouTube and type in Dr. James Tour, and my channel will come up. And so that 125,000 views in 3 weeks. It's not like Kim Kardashian, but for scientists, it's trying to get it out there.
Yeah. And actually at our institute, we have a program for high school science teachers in 30 different school districts. So those are fully booked every Saturday. Our grad students and postdocs learn outreach, and we give kits to the schools and show where in the California curriculum these experiments fit and what can be taken out of other classes, essentially, because zero-sum game when you're teaching high school. And so we have, we try to engage the community in that way. And I think a number of comparable institutes around the country do things like that as a way to get, we have the camps and all, but that's a very limited population, and they're pretty much, with you already.
Well, let me pass it to Dr. Gomez so that he can ask a question or two from the chat. I know we're running close to the top of the hour, so. Oh, I think you're muted, Cisco.
Sorry about the dog barking. We got a couple of questions here. Can the nanobiosensors get through the blood-brain barrier innately?
So actually, yeah, I just have some colleague and a new colleague in neurology who wrote, "Hey, I need something to get through the blood-brain barrier." That's a really tough one, right? There are, limited ways to get through. There are examples in nature, like the parasite for African sleeping sickness has, is driven motion with this little spiral thing in the back that it can turn around and use as a drill to get through the blood-brain barrier, is how it operates. But it's rather limited now what we can do and what we can do selectively. So yeah, the brain diseases are tough.
Yeah, I would follow that up, but why not just put it directly in the CSF then? Yeah.
So again, there are sort of limits to targeting in the brain. When we first did this gene editing, the Rett's syndrome foundation people came to us, but the exact access to where you want to be can be difficult. So that's a lot of the limitation right now of nanomedicine. You target tumors often just by virtue of there's slightly different chemistry. Maybe the pH is shifted a little bit, and they're leaky vasculature, and things that are encapsulated, like the brain or like pancreatic cancers, are much more difficult.
Okay, somebody else is asking, undergraduates learn more about the basics of nanotechnology in healthcare. I guess you covered that with the information you gave out.
Well, I think, actually, let me comment on that. So I teach freshmen here, and what I have them do starting in the very first class is go to seminars, read papers in the current literature. And now so many seminars like this are online. There is an opportunity to watch, a very large number of top people in the world. We host these lectures. Well, in California, they're 4 or 5 in the morning, depending on the time of year. They're actually broadcast out of Beijing at 8 p.m. and we have 300,000 people attend them live every week, even though, they're online a couple of days later to watch on, YouTube and other platforms. So, if you're interested, look at ICANX as one example. And we've had, most of the top people in the field speak there. And then, just keep an eye out there. There are opportunities all around us for following what people are doing that I think, we benefited from the pandemic and having set up all that.
We just go one more then, Cisco?
Yeah, we have questions both our speakers. How do you see your research fitting or affecting our world today and in the future? It's a pretty broad question. I guess I'll lead you guys to just answer. What would you see the biggest change to be in the next 5 years? Let's just make it more narrow, or we can talk forever.
Right. I think a couple of there's several areas where nano is really poised and beginning to make big advances. One is in medicine, another's in the environment, to be able to provide mechanisms for cleaning up the environment, and the third one, of course, is in enhanced materials, the strengthening of materials. That's really beginning to transition now.
And the batteries, I think, will be a huge change in the near future. Dr. Tour, Dr. Weiss, anything to add, boss?
Yeah, I'm hoping that more and more innovations in medicine come through our field. I mean, we can thank nano for the COVID vaccines as an example. That those are the basis of the ones that have been protecting us, and there are even more opportunities. As we said, that's the scale of function in biology. And so as we learn more and as we keep it simple, I think is one of the keys. That's how you get through approvals. Then hopefully we'll have other opportunities. I think there are more vaccines coming as well, just down that, not from our lab, but from others. And then I think, nano has a much bigger opportunity, as I said, in terms of communication skills. And so it's incumbent upon us in the field to look at the, again, pardon the pun, bigger picture. And, where are fields who need us? And, just, the example at UCLA, pulling in people from all these different areas and having them share their problems and then putting teams together, that seems to be how our field is constructed and not how any others are. And so trainees ought to be looking for, what interests them beyond nano, and then, learn that area or those areas as well, just as, we've been able to do here.
Okay, so we are at top of the hour, so we should probably let these guys chat because they've got other things to take care of, classes to teach and seminars to lead.
Thank you so much. What a wonderful opportunity. And yeah,
Right.
terrific. Thank you.
It was great.
Question.
Thank you very much, everybody.
Chris, do we want to keep the conversation going maybe with the people who are still in the room here, or?
Yeah, I think Linda suggested that what we can do, we can keep the meeting open. It's I can split, and I'm going to